is the 26th?
Yes.
All right. Are there any questions?
When do we get to see our, test scores?
When I feel like it. Picturing, I'd like to think Friday. Any other questions? And the spring break starts the 5th?
It's Monday and Tuesday, that's the only class we have.
Okay.
Monday, Tuesday.
Even better.
Yeah. All right, I believe we last left off where we were doing centripetal motion, but I didn't actually derive the formula. We got as far as slinging stuff. I don't know if we actually got to do a math problem.
No math problems.
Okay. So it's justified. Something that shows better. That's supposed to be part of a circle. I have an object that is traveling at a constant speed along this arc. Establish coordinate system here, I hat and j hat. And I know that the velocity is tangent to the path, and we demonstrated that is when I spun it in a circle and I let go, it just traveled in a straight line at that point, tangent to the path. So if I spun it in a circle like this, going counterclockwise, if I released it here, it would go straight. Or it would actually go downwards in a projectile motion, but it would not veer left or right. And we know from Newton's first law and second law that an object will want to maintain its velocity unless it has some outside force acting on it. So at this point right here, the direction of the velocity is that way. At this point here, the direction of the velocity is that way. So what I do is, if that's the center of the circle there, so center, so some radius r, we'll go with the lower r. And this angle and this angle are the same. I know acceleration is the change in velocity over change in time, so let's actually figure out what the velocity is at these two moments and go from there. So initially, if this angle right here, it turns out that if this angle here is phi, then this angle here is also phi. I know that since the velocity is tangent to the path, that is a right angle there. And I can dot, 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 that is a right angle there. And you could look from similar triangles or several ways of doing it, but I'll just cut to the chase. That angle there, which is the same angle as there. So its initial velocity would be the magnitude of v and an angle of phi in polar form. Or, putting it into rectangular form, v the initial velocity is v cosine phi plus v sine, v cosine phi I hat plus v sine phi j hat. Now, you can make a symmetry argument or go through the same similar process that if this angle is phi, that angle is phi, then this would have an initial, final velocity of v negative phi. Or, in rectangular form, surely one of these markers is dark enough to see. V cosine phi I hat minus V sine phi j hat. Questions up to you? Tape?
For the very top equation, is that just velocity times the angle?
Oh, here?
Yeah.
That's polar form where I give the magnitude and direction.
Okay, yeah.
Other questions? All right, so acceleration is the change in velocity over the change in time. Well, the change in velocity is v final minus v initial over however much time it took to get from this position to that position. So first, let's just do final minus initial. I have in rectangular form, this is v cosine phi I hat minus v sine phi j hat minus my initial velocity, which is very similar, v cosine phi I hat plus v sine phi j hat over the amount of time it took. So all I'm doing is just plugging in our rectangular forms for the final velocity and the initial velocity. Distribute the minus sign, add, and so we end up with, well, the cosine phi's are going to cancel out, but we'll end up with negative 2 v sine phi j hat divided by time. Small angle approximation. How many of you are familiar with it? It'd be nice if I have that chart here. That's in the other notebook. All right, so we're gonna, I need to do two other things and then come back to this. Let's first talk about what a radian is. Or you tell me, what's a radian? Oh, Nick.
Is it a part of the radius that goes around the circle?
What do you mean by that?
Like, one radian, like, the 3.14, one radian is around it. It takes 3.14 radians to get around the whole circle.
Half a circle.
Happens, yeah.
How did they get that? How did they define a radian? What's wrong with 360 degrees for a circle? What's wrong with 360 degrees is that why 360?
Why not?
It actually comes from the Babylonians. That's how far back it goes. There's something special about the number 60. And if you think about it, the Babylonians had a base 60 system instead of the base 10 system that we use. But 60 actually is a nice number in the fact that there's so many things that go into it. It is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. So it's divisible by 12 different numbers evenly. So somehow they connected 60 with, I think they gave it some religious significance. And the equilateral triangle also had some significance in the fact that because of, well, symmetry, every side is the same, every angle is the same. They went ahead and associated 60 with the angle, which we now call degrees. And if you take one of these equilateral triangles and then you sort of put them together, they fit very nicely into a sort of a complete set there. And so we'll have 1, 2, 3, 4, 5, 6. 6 times 60 is 360. That, in essence, is where 360 degrees comes from. There was a big push in mathematics in the 17th and I think primarily 18th century to get rid of as much man-made influence as possible. They figured there's got to be something unique to circles so that we can come up with a system that's not reliant upon what somebody came up with several thousand years earlier. So they realized the formula for a circle was, the formula for the circumference of a circle was the same no matter what the circle was. And what is the formula for the circumference of a circle? Which means that if I have 2 pi of whatever the length of the radius is, I can go all the way around the circle. So if I take one radius, it's going to go that far, so that's r. I take 2 of them, it's going to go that far, and I can keep wrapping it around, and it'll take a little more than 6 to make it all the way around. So if this is true for any circle, that means that this angle here would be the same for any circle. If I take the radius of any circle, take that radius, wrap that length around the edge, that the angle that is subtended is going to be the same no matter what the circle is. That is a radian. So if the arc length is the same as the radius, then we have 1 radian, or also legitimately an angle of 1. Radians are a unitless unit. Questions here? So in general, if I take a circle, I have some arc length here, which I'm going to label with an S. I have a radius and I have an angle. What is the mathematical relationship between S, theta, and R, assuming theta is in radians?
They're the same.
Say it again?
They're the same?
No. If S equals R, then theta is 1 radian, but looking for a more general relationship there. For a specific circle, I hope R is not. All right, let's piece it together. For a specific circle, R is a constant. So if I want to plot the arc length versus the angle. So if the arc length is R, I know that the angle is 1. So put that in. If the arc length is 2r, what is the angle?
2.
If it's 0,
0.
and we end up with this linear relationship. There's a linear relationship between s and theta. That's theta down there. Matter of fact, the only difference between it is this letter r. So the arc length is equal to the radius times the angle. Always think of standing rule only. So that is the relationship between the arc length r and theta. So if I come back to my triangle here, this distance right here, which I will cleverly label s, is going to be equal to the radius of the circle times my angle, which is 2 phi. I know my speed is distance over time, and so, well, that's the distance I travel, divided by t, which is the amount of time it takes to do it. And I put it down somewhere. There we go. So I know that my speed is equal to the distance over time, which is 2r phi divided by t. And actually, I want to solve for t. So t is equal to 2r phi over v. And if I plug that into here, I now have 2v sine phi j hat divided by 2r phi over v, which is, well, the 2's cancel out. I'm left with v squared sine phi j hat over r phi. Nope, I lost my minus sign. There we go. Minus. Now the small angle approximation. And if you've never seen it before, I would suggest that at some point just play around with your calculator, make sure it's in radians. But if, let's see, we're going to get rid of this space here. If an angle is small. Now this notation is that if phi, or that's a theta, if theta is much less than 1, if you need something more specific, usually if it's less than 10% or 0.1, because I have no units after it, this has to be in radians. So if the angle is much less than 1 radian, then the sine of theta is approximately equal to the tangent of theta, which is approximately equal to 1. Sorry, I lied on that one. Approximately equal to theta. And anyone have a calculator out that they can quickly just, so if theta is equal to 0.05, what is the sine of theta? And again, this has to be in radians. .0499. And if theta, and the tangent of theta? .05. So you can see that they are very close to each other in just this one example. So all I need to do is make sure that my angle there, my 2 phi, is small. Well, since I want to figure out the acceleration, really, I want to find the acceleration at this point right here, I need to make these angles as small as possible. So as phi goes to 0, so as phi approaches 0, it's not equal to 0, it's just really close to it. As phi approaches 0, we definitely are dealing with a small angle there. And the sine of phi becomes just phi. So if phi is small, then this equals negative v squared phi over r phi j hat. Phi's cancel out, and we're left with negative v squared over r j hat. The magnitude is v squared over r. The negative j hat means, in this particular case, well, actually in all cases, but negative j hat is this way. In other words, it's pointing towards the center. No matter where I am in the circle, that point, the acceleration is always going to point towards the center. So let's generalize it. There's also some, what I think a very slick calculus derivation of it. Where you start out with r, the vector from the center to where an object is equal to r cosine theta I hat plus r sine theta j hat, and then take the second derivative with respect to time, and it comes out of that. So to generalize it, since it's always pointing towards the center, and I don't think I've officially introduced the r hat, done I hat, j hat, k hat. I don't think I know if I've done r hat. Dominic, question first?
With the thing you're doing, is that f double or r double prime?
That when you take the derivative with respect to time, you can use a dot over it to represent. This would be the same as